Welcome to this session of graph theory. Here we are going to discuss coloring and its applications. In our earlier sessions, we have discussed the coloring of graph, mainly vertex coloring of a graph and edge coloring of a graph. Today we are going to discuss this 5-color and 4-color theorems of planar graphs. The coloring problems dates back to 1950s on real-life situation of coloring the map of the countries of England. By coloring of a map, it is meant that two adjacent regions no two adjacent regions receive the same color, or two adjacent regions receive different colors. By adjacent regions, we mean that regions having a common edge between them. Two regions having common vertex are not regarded as adjacent regions. Coloring of regions is also referred to as map coloring, in view of the fact that in an atlas, countries with common boundaries are always colored with different colors. Consider this following. Here it illustrates the coloring of regions of a planar graph. Here you can see that no two adjacent regions have same color. Here this region is colored red, and the regions adjacent to it are these two regions. If it is taken as 1, 2 and 3 are adjacent. Whereas even though this region 4, which has a common vertex with the region 1, it is not considered to be an adjacent region of this region. Okay, prior to going the coloring problems, we will discuss a little bit on planar graphs. Planar graphs. In general, graph can be represented by more than one geometrical drawing. In some drawings representing the graph, the edges may intersect or cross over at points which are not the vertices. In some others, the edges may meet only at the vertices. Suppose if you are drawing a graph like this with 4 vertices, and we are going to draw the complete graph. Here, A, B, C, D. If you are drawing this edge like this, this edge seems to intersect at this point. Okay, so in this representation, the edges may cross over. That is where the edges may intersect at points which are not vertices of the graphs. So, like that, it is what is meant by the edges may be intersecting at points, or crossover may be happening which are not vertices. A graph is said to be planar if there exists some geometric representation of G which can be drawn on a plane such that no two edges intersect. In our earlier case, if we are considering this graph, complete graph on 4 vertices, here the edges cross over or intersect. We can draw like this also, where the edges does not cross over at all. So it is called planar representation. A graph that cannot be drawn on a plane without crossover between the edges is said to be non-planar. A drawing of a geometric representation of a graph on any surface such that no edges intersect is called embedding. Such that if we can find a drawing such that no two edges intersect, then it is said to be an embedding of a graph, planar embedding, or planar representation. And if it has a planar representation, then we call that graph can be planar embedding. Currently, we have another definition of this planar graph. A geometric representation is planar if there exists a graph isomorphic to G such that it can be embedded in the plane. Otherwise, it is said to be non-planar. An embedding of a planar graph is called a plane representation of graph G. Embedding of a planar graph on a plane is called a plane representation of that graph G. Consider these graphs. Here I have already drawn this point. This is not a planar embedding because why? The edges E and F here crossover. Crossover between E and F happens here. So it is not a planar embedding. Here no edges crossover, and this is a graph is planar and it is a planar embedding. This is also a planar embedding, which is these are all isomorphic representations. Now consider these two graphs. Same isomorphic graphs. Graphs with 8 vertices Look at this. Here the edges cross over. So it is not a planar representation, whereas this is a planar. So the graph, which is an isomorphic representation, is planar planar embedding is there. So this graph is planar. We can have a representation of a graph in a plane such that no two edges cross over. Such representation, if such representation is possible, then the graph is referred to as a planar graph. Consider this isomorphic graphs. These are all isomorphic representation of same graph. Here we cannot find any such embedding such that planar embedding. So this graph is non-planar. Okay. Now we have some important results on this planar graphs. That is K22 and K23 are planar graphs. The complete graph on 5 vertices is non-planar. K33 is non-planar. Usually this K5 and K33 complete bipartite graph on 3 vertices. These are usually termed as Kuratowski's first and second graph respectively. Kuratowski's theorem is considered as a fundamental theorem in the study of planar graph. The theorem states that a necessary and sufficient condition for a graph to be planar is that one necessary and sufficient condition for a graph G to be planar is that G does not contain K5 or K33 as subgraphs. That is, if a graph contains K5 or K33 as a subgraphs, then it does not have any planar representation. We have seen that in planar representations, the region has been divided into a number of parts. The number of parts is called as regions or phases. That is when we are representing a graph on a plane. If a graph has a planar representation, the plane has been divided into a number of parts. And those parts are referred to as regions or phases. The number of edges that form the boundary of a region is called the degree of the region. That is, if we have considered this graph divides the outline into 1, 2, 3 regions. So this is called regions or phases. And the number of edges that form the boundary of the region. That is, if here this region 1 boundary is formed by 3. So this is the degree of the region 1. And this is 2 is the degree of the region. 3 is the degree of the region 2. And this region 3 has degree 4. Now, an important note that we have to keep in mind is that if a tangent edge is a part of a boundary of a region, then this edge is counted twice while determining the degree of the region. We will see with an example. Consider this graph. Here the graph with 6 vertices, and it is divided into 6 regions. Region 1, region 2, 3, 4, 5 and 6. This region 1 to 5 are termed to be bounded by, because it is bounded by normal sense itself, bounded by some edges. Whereas region R6 is exterior or unbounded region. The boundary of region 1 is made up of 2 edges. So the degree of region 1 is 2. The degree of region 2 on 2, 3, 3. And same for the degree of region 4. Whereas consider this degree of region 5, it is bounded by 1 edge. So it is 5. And whereas this degree region 3, 1, 2, 3, and this edge, tangent edge is there. It is counted twice. So it is 5. So now considering the sum. And consider this remark. Degree of sum of the degrees of the regions, degree of R1 plus degree of R2 plus degree of R3 plus R4 plus R5 plus R6. Oh, I forgot to tell here. The degree of region 6 is 1, 2, 3, 4, 5 and 6. Okay. Is equal to 20, which is twice the number of edges in the graph. We have already seen that the sum of degrees of a graph is twice the number of edges in a graph in handshaking property. This is also here the degree of regions which is analogous to the handshaking lemma is true for all planar graph. Okay. Then the concept of dual of a planar graph. Consider a connected graph G and a plane drawing of it with regions R1, R2, etc., including the exterior region. Construct a graph G star as follows. Choose points inside R1, R2, etc., so that points are P1, P2, P3, etc. These points are going to be the vertices of the new graph that we are going to construct newly, G star. If two regions Ri and Rj are adjacent, then draw an edge Ek star joining the points Pi and Pj, because we have put Pi and Pj in the centers of this Ri and Rj. If two regions Ri and Rj have more than one edge in common, draw the edge Ep star corresponding to each edge. If there are two regions, these Ri and Rj have two common edges between them, then draw two edges between Pi and Pj. For a pendant edge in Rk, draw a loop Ek star at Pk. Okay, so the graph G star so constructed is called the dual of the given graph G. Consider this graph. Here we have three regions R1, R2, R3, and the edges are E1, E2, E3, E4, E5, E6. So we have put this P1, P2 and P3. And corresponding to this, R1 and R2 have one edge in common. So that is put like this. Then R1 and R3 has two edges in common. That is put like this. R1, R2 and R3 has two edges in common. That is put like this. And there is one edge, pendant edge in R3. So it is put like a loop. This is if it is the G, then it is the G star. G is the planar graph and this is the planar graph, which is a dual of this graph. Euler's fundamental theorem on planar graph. Euler gave the main results connecting the number of vertices, number of regions and all in a planar graph. A connected planar graph G with n vertices, m edges has exactly m minus n plus 2 regions or faces in any one of its diagrams. That is, if regions are considered to be R, then it can be stated that R equal to m minus n plus 2, where m, sometimes we might have used m as to be q, n equal to p, then R equal to q minus p plus 2. Okay. Then the consequence of Euler formulas we have this m is greater than or equal to 3 by 2 r and m is less than or equal to 3n minus 6. Also, every connected simple planar graph G contains a vertex of degree less than 6. Whenever G is a planar and connected, a simple planar connected simple graph, then G can have at most vertex degree of 6. Then we are going to this 5-color theorem where the application of coloring starts. So far we have done this planar graphs just because to have some idea of the terminologies that we are going to use with. 5-color theorem. Every vertices of a simple connected planar graph can properly connected with 5 colors. That is, if G is a simple connected planar graph, then every vertex can be colored with at most 5 colors. We will see how it happens. If the number of vertices of G is less than or equal to 5, then obviously we can color with any of these 5 colors. So it can be 5 color. Assume that it is trivially true for all n which is less than or equal to k. Here we are using the process of mathematical induction to prove the theorem. Consider graph. Then if it is true for all n vertices n less than or equal to k, then we are going to prove it for n equal to k plus 1. As a consequence of Euler's formula, every simple connected planar graph contains a vertex of degree less than 6. As the maximum degree of a vertex in a G can be 5. Let it be named V. Consider a subgraph H of G such with vertex V. Consider a subgraph H equal to G minus V, which is obtained from G by deleting V. Therefore, H has k vertices because now we have taken G to be with vertices n equal to k plus 1. When we are deleting one vertex from H, it has k vertices. So, it is 5 colorable. Since the degree of vertex V is at most 5, we have at most 5 neighbors. We cannot have any more 5 neighbors, any neighbors more than 5 neighbors, because why? Then the degree will be increased. Suppose we have 4 or less neighbors, then the neighbors can be colored with any of the 4 different colors and we can be assigned 5th color. So, it can be used, which has been used as part of this H. So, G can be colored with 5 colors, for which with the H has been colored because H has already been colored with these 5 colors. Hence, G is 5 colorable. So, now assume that if G has 5 neighbors. First, we have assumed that G has 4 or less neighbors. Now, we are going to see if G has 5 neighbors, what happens. Let the neighbors be V1, V2, etc. V5. Arrange them anti-clockwise around V as shown. Then at least 2 of them must be non-adjacent. Why? If all are adjacent, if all are mutually adjacent, then what happens? These 5 vertices are mutually adjacent, implies it constitutes a K5. If a graph, from the Euler's theorem, we know that if a graph contains K5 or K33, then it is non-planar. So we have assumed this graph G to be planar with vertices and n equal to K plus 1. So this at least 2 of them must be non-adjacent. Let's take it to be V1 and V3 be non-adjacent vertices. Now we are going to construct a new graph G dash. By merging the edges, here we had this V1 is merged here and V2 V3V is merged. So by merging those edges means we are the vertices come to the common point. And so we will be left with such a condition. The V1 is coming here, V3 is coming here, and we will be left with such a condition. Okay? And thus G will be left with K plus 1 minus 2. For why? Because we have taken G to be with vertices K plus 1. And now we are merging these 2 vertices to 1. So that 2 vertices are being deleted. So number of vertices is K minus 1 vertices. Hence G dash is K colorable. Assign this color alpha to this one, V1, V3, and alpha 2 to V2, alpha 4 to this one, and alpha 5 to this one, V5. And now if we are unraveling this vertex to be this V1 here and V3 here, we can assign any of these colors alpha 3 to any of these, both without disturbing other colors, which will produce a G to be a G with 5 colors. Okay? And thus we get G is 5 colorable. Hence we have taken this G was taken to be with n equal to K plus 1 vertices and G is K colorable. Where with if a graph with n minus 1 K, that is we have taken this G is 5 colorable. That is, if G is equal to n vertices with n equal to K plus 1, then is 5 colorable if a graph with n vertices which is less than or equal to K is 5 colorable. Hence, by induction process, it follows that G with a graph with n vertices is 5 colorable. Okay? That is, any planar graph with n vertices is phi colorable. Now we are going to define a k colorable face of k colorable f and k colorable v. We define this k colorable f if its faces or regions can be colored with k colors, such that no two regions with the same with a common boundary can have same color. And k colorable v means normally the vertex coloring. Yes, k colorable of graph in the usual sense that of vertex coloring of vertices. Now we are going to have this 4-color theorem, which is the most famous coloring theorem in graph. A simple connected planar graph is 4-colorable. That is, we require only 4 colors to color a planar graph. Equivalently, every map can be colored with just 4 colors. Why this map? Every map is planar graph. That is, map is 4-colorable F. That is, faces can be colored with 4 colors. Consequence of the planar 4-color theorem is that if G is a planar graph and G star is a dual of G, then G is k colorable, vertex colorable, then G star is k colorable, face colorable. That is, if we are having this G with vertex colors 1, 2, 3 colors are using here: blue, black and red. Now we are taking this G star, dual of this G. This vertex can be colored with, here we have it equal to 3. Now consider this planar graph. Considering this planar graph, we are considering this dual of this graph. From this dual, we can color using the same 3 colors. Okay. If G is planar graph and G star is a dual, then if G is k colorable with vertex of G is colored with k colors, then the faces of G star can be colored with the same k number of colors. Now we are going to see this Welsh-Powell theorem. If G is a graph of order n and has a degree sequence d1, d2, d1 greater than or equal to d2 greater than or equal to etc. dn. What is this degree sequence of the graph? When the degrees of the vertices are arranged in a non-decreasing order, then it is said to be the degree sequence of the graph. If G is a graph, this Welsh-Powell's theorem states that if G is a graph of order n and having the degree sequence d1, d2, etc., where d1 greater than or equal to d2 greater than or equal to etc. dn, then the chromatic number of G is less than or equal to 1 plus maximum of the minimum of di I minus 1. We are using this greedy algorithm to the vertices in the non-increasing order of degree. When we color the vertex has at most minimum of di I minus 1 Euler neighbors, so that at most many colors appear on its Euler neighbors. Hence, the color assigned to bi is at most 1 plus minimum of the di I minus 1. This holds for every vertex. So we maximize over I to obtain the upper bound on the maximum number of colors used. That is why this chi of G is less than or equal to 1 plus maximum of the minimum of di I minus 1. We will see how this Welsh-Powell algorithm works. Find the vertex degrees of every vertices. And list the vertices in the order of decreasing degree. Then color the first vertex with color 1. Move down the list and color all the vertices not connected to the colored vertex with same color. That is, if we will see with an example. Then repeat the step 4 on all uncolored vertices with new color in the decreasing order of the degrees until the vertices are colored. By starting with the highest degree, here we are starting with the highest degree vertex. Then we are coloring with the next vertex which is not adjacent to the first vertex that is being colored. Then we are continuing the step only. Okay. First, we are starting with the first degree vertex with maximum degree and coloring it 1. Then moving down the list, we are coloring the vertices that are not connected to the colored vertex, and we are then repeating this step like that. By starting with the vertex with highest degree, we make sure that the vertex with the highest number of conflicts can be taken care as early as possible. Because why? If we are taking the vertex with maximum highest degree, then it is mostly adjacent to most of the vertices. Here we are using that. Apply Welch-Powell algorithm to the given graph. Here we have vertices from A to JK up to K, 11 vertices. Here it is here is how this, see, here 1, 2, 3, 4, 5. H has maximum degree 5. 1, 2, 3, 4, 5. K also has 5. Then G has 3. F has 2. E has 2 degree. This J3, 1, 2, 3. Here also 1, 2, 3, 1, 2, 3, 4. 4 degree, 1 degree, 2 degree, 2 degree. Arranging the vertices on the order of the sequence, we have this H, K, D, G, I, J, A, B, E, F, C. And we are coloring this H. Because H is the vertex with maximum degree and H we are coloring it as red. Then we search for the next vertex which is non-adjacent to H. Here we cannot take, because on searching each K is adjacent to H, we cannot color. Then D, which is non-adjacent to H, so we can color this also red. Now just check for G, which is we cannot color this one with red. And I which is adjacent to H, so we cannot color with H. Then A cannot be colored with red. B cannot be colored with red. Why? Because B is adjacent with the D, so it cannot be colored with red. Then E, which is next one, which we can color with red. F cannot be colored red because it is adjacent to E. And C cannot be colored red because it is adjacent to D. So we can color only three of these vertices with same color. And the resultant graph is like this. Now, ignoring the vertices that we have already colored, we have left with only these vertices. K, G, I, J, A, B, F, C. So now we can color this K. K is the vertex with maximum degree, and so we are going to color it with green. Now we have that G. We cannot be colored with green. Why? Because G is adjacent to K. Continuing the process, I can be colored with green, whereas J cannot be. A can be colored with green, B cannot. F can be colored with green, and C can be colored with green. And the resultant graph looks like this. And now we have vertices, which all vertices are left with G, J, and B. This can be colored with any color because they are neither of them are adjacent. So any colors can be used to color these vertices. So using this, blue is used, and this final graph is like this. So what the result we got is, using Welch-Powell's algorithm, it is possible to color the vertices with only 3 types of colors, which is the max optimal solution. Now we will see what is polygon triangulation. Triangulation of a planar graph G in which we will see this polygon triangulation. A triangulation is a planar graph G in which every region is bounded by a triangle. So that is, if every region is bounded by a triangle, then it is said to be a triangulation. If G is a planar graph, and if every region is bounded by a triangle, then it is said to be a triangulation. Remark: every embedding can be extended if we are having a planar embedding, it can be extended to a triangulation on the same set of vertices. How? We need to add only edges. Consider this planar graph. This is a embedding and polygon triangulation obtained by diagonals. Polygon triangulated diagonals. A planar embedding is called a polygon triangulation if it is a triangulation and all the vertices lie on the outer circle. Here all the vertices are on the outer circle, and it is it is a triangulation. That why? Because every region is bounded by a triangle, and this is a polygon triangulation by diagonals. Polygon triangulated by diagonals. A triangulated polygon with n vertices has 2n minus 3 edges on n on outer circle and n minus 3 on n minus 3 diagonals. Every triangulated polygon is 3 colorable. Every triangulated polygon has a vertex of degree 2. An art gallery problem. It is an application of coloring, this polygon triangulation. Every n degree vertex, n degree art gallery can be guarded by n by 3 guards. Suppose P is a polygon on R2 with n vertices. On assumption it to be the floor plan of an art gallery, how many guards are required to guard each point inside? Here we are just drawing. If from the floor plan, it means that the graph is planar, and we can just triangulate it. Polygon triangulation is applied here, and then we are using the coloring process. From every triangular we have this a triangulated polygon is 3 colors. P being planar, first triangulate using diagonals. Then the resulting triangular polygon is 3 colorable. With some color class will have n by 3 elements. Place the guards at the vertices of their color. Example, if we are having these figures like this, we can put like this, triangulate this. Every regions are triangulars. And this, according to this polygon triangulation, we need only 3 colors. Welsh Powell's algorithm states that we can color it with 3 colors. And here we can put the number of guards with lower integer n by 3 like that. Okay. Now, so far we have discussed this. What is a planar graph? What is 5-color theorem? That is, every vertices of a planar graph can be colored with 5 colors, at most 5 colors. And 4-color theorem, and Welsh Powell's theorem, and polygon triangulation, and art gallery problem. Thank you for watching. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.